Good afternoon, everyone. So this is a joint work with Kevin Bluto, Chris Bout, you probably heard about him today, right? And Leopoldo Catania. So the European crew is on the table here, so do not hesitate to come and discuss with us about this study. So I start with the motivation. So on this plot you see the log return of the SMI index for a period ranging from the 90s to a period after 2000. And what is important, I think, from a risk management viewpoint is to model the variability of this time series, namely its volatility. And typically what you want to capture with an econometric model is the so-called volatility clustering, i.e. the fact that you have small blocks of small volatility followed by block of high volatility. And the seminal model, which has been developed by Boleslav in 1986, to account for this is the GARCH model. So in the GARCH model, you try to express YT, which is the log return, given an information set, IT minus 1, with a conditional distribution, which is standardized and which depends upon a conditional variance. And the conditional variance here is key. It's a linear function of past square return. So if you have a high positive or negative shock in the past, it translates into a high volatility for the next period. And if you are currently in a high volatility period, so HT minus 1, it translates into a high volatility tomorrow, right? And then seminal paper with a normal distribution for the conditional distribution, parameterized by parameter psi here. Then this will be relaxed to account for skewness or heavy tails in the distribution. So this is nice. But actually what has been observed is that when you have a structural break in the dynamic of the volatility process, then the estimates of the GARCH model are biased, and this leads to very poor forecasts for risk predictions. So here is an example. I've simulated 500 points, data points from two GARCH models. So in the first GARCH model in blue, you have I decided to take three parameters with a given unconditional variance for the process, and this process is covariance stationary, so the volatility does not explode, and it is followed by another GARCH process where basically the unconditional variance is 2 times higher, but still it is covariance stationary, right? So the process basically is not exploding at all. Now, if you assume that actually you observe a single process, so no structural break, and you try to estimate this model, what you get is a very, very high persistence. Basically, you get an integrated GARCH model. And this has implication for the forecast. So one way to deal with that is to account for the structural break via a latent, unobservable variable following a Markov process. And this is MS GARCH model. Right? So several parameterization have been proposed in the literature, and the team follow the parameterization by Haas, Mitnick, and Paolella. So here, that's the same setup than before, but YT, the distribution on YT is conditional upon this state variable ST, which can take several value from 1 to capital K, which is the state in which you are. And this state is not observable, right? But given the state, conditional on that state, you have a distribution for the return, and typically you have a given volatility process, HKT, right? So that's the conditional volatility at time t in state K. And this process follows a GARCH type model, right? So in each state, you have a GARCH type process. Here, I gave you the standard GARCH 1.1 process, but you can imagine any asymmetric model. And therefore, the variable ST dictates in which state you are, and therefore in which conditional volatility process you are in order to take the volatility for the YT process, right? And then you parameterize the Markov chain by a transition matrix, capital P. So the approach by us is very, very nice because it is tractable, i.e. you can estimate it by maximum likelihood. You don't need necessary MCMC techniques, and then you have interpretability of the parameters. So in one state, you can see what is the persistence, what is the leverage effect, etc. And several papers have shown that it is important to account for those structural break. Marcucci, for instance, or Bowens on others. So they report better performance for this class of model. But still, when they do the out-of-sample analysis, what is done usually in academia is that they take a couple of time series, right, and they test the new model on that. We take another angle in this study. And those class of models are quite time-consuming to estimate. They are more complex, obviously, than GARCH. So the question we want to ask in our study is that, are they really relevant in practice? Right? From the academic studies, we cannot really conclude this because they don't span enough time series. So we want to investigate this. That's why we perform a large-scale performance study over hundreds of stocks, several market indices, and currencies, right? And we want to compare how they perform with respect to the standard GARCH model that you find in the literature. So that's the first question we are trying to answer. And the second one is to investigate whether we should integrate the parameter uncertainty in the forecasts, right? So with MLE, maximum likelihood estimation, you get 1 point forecast. But you could run a Bayesian estimation of the model and via the predictive distribution account for the parameter uncertainty in the forecast. So the second question we want to answer is that whether the Bayesian estimation is better in order to estimate and to forecast risk with these models. So we run the analysis over 400 stocks taken from the S&P 500. 11 major stock indices and 8 major currencies. The model we estimate are single regime and two-state Markov switching models. We take symmetric specification for the variance process, asymmetric specification. JGR is really easy. I mean, in our study, we did several sensitivity analysis with the eGARCH, for instance, but the results are similar. So we go for a more easy to estimate model. And then normal, the standard and student T distribution to account for fat tails, and the skewed version of these using Fernandez and Steele, right? So we have very flexible models for single regime and very flexible model for Markov switching, and the goal is to see whether Markov switching add any value. In terms of estimation, standard 1,500 points. We use a rolling window approach on daily returns, and we perform maximum likelihood and MCMC estimation. Everything is implemented in the MS-GARCH package that will be described by Kevin afterwards. And for the forecasting, we run the study over 2,000 out-of-sample points, and we currently focus on 1 day ahead forecast, and we focus on the left tail of the distribution. Right, so let's have a look at the results. First, for the value at risk. So what we do, we want to forecast a quantile, right? So we do the standard back test. We use the DQ test by Engel-Manganelli, which is a test for VAR, which has been proven to be powerful. And for each time series, we fit the model, we compute the out-of-sample performance, and then per asset class, we report per model the frequency of rejections at the 5% level, right? And we correct for false positive using FDR approach. We test and try to answer whether MS outperforms single regime and whether MCMC outperforms maximum likelihood. We did that for other tests, results are similar. So that's the first table you will find in the paper, right? And here I will focus first on stock, and we focus on 1% value at risk and the 5% value at risk. And what you have in this table, that's the frequencies of rejections, right? So let's ask first the question, is Markov switching better than MCMC? So you see on the left-hand side all the specification for the GARCH and the distribution, the conditional distribution. And on top, you see MCMC ML and Markov switching and single regime, right? So the first question is to compare the red part with the blue part, i.e. within the MCMC class, or MCMC estimation method, do we see something lower for Markov switching? And this is clearly the case, right? And in light gray, I don't know whether this is clear on the screen, we perform a significant test. So we can conclude that Markov switching significantly outperforms single regime in the space of with the MCMC estimation strategy. Results are the same for maximum likelihood, right? And now the second question we want to ask is that whether MCMC, so whether when you integrate parameter uncertainty in the forecast, does it really improve the risk forecast in terms of backtest? So we are comparing the red box against the blue box, and what you see in terms of the star would report the lowest significant percentage for per line, we see that most of the stars, well, actually in this case, all the stars are really for MCMC. So MCMC adds value over maximum likelihood, right? So accounting for parameter uncertainty is important in this case. We can note other features like JGR is preferred, so you need asymmetry in the variance process for stocks. You need students, so you need to account for fat tails. This is not surprising, right? But this is the case for Markov switching as well, not only for single regime. Skewness is preferred. And in terms of backtest, what is striking here, over 400 stocks, the level of rejection is very low for the single regime JGR student T and skewed student T models, right? So this model performs quite well, while still the MS-GARCH model adds some value, right? So that's the first way we tackle the two questions. In terms of stock indices and currencies, that's not surprising, right? Because those indices and those asset class exhibit less excess kurtosis and less asymmetry. The results in terms of numbers are in the same direction, but they are less significant. Now we focus really on the left tail, on the full left tail distribution. So we do not stick only to the quantile, but we really look at the mass of the distribution below the quantile. And for that, we perform a pairwise comparison on the left tail between Markov switching and single regime models. And we use the CRPS measure, which actually is a measure between the forecasted CDF and the realized CDF. We do that for Markov switching and single regime. We compute the differential, and then we perform a Diebold-Mariano test on this differential. Then, if a negative value is observed, this means that Markov switching outperforms. And again, we report in light gray significant results, so significant outperformance for the Markov switching class. We report here only MCMC results, but similar conclusions are obtained with the maximum likelihood. So this is typically the table you'll see in the paper. Again, light gray indicates significant result, negative significant results. And for the Markov switching, we see that for almost all specification, it outperforms the single regime class. Again, JGR, student, skewness is preferred. Now, when we dig a bit further into the results and we try to really observe one model against another model, i.e., to see what makes really Markov switching attractive compared to single regime, we obtain the following table. So on the left-hand side, you have the model specification estimated by the Markov switching approach. And on top, you have the same models, but estimated with a single regime mechanism. So the basic model, if you want, right? And the table reports, again, the Diebold-Mariano test statistic of the differential. A negative value favor Markov switching specification, whereas a positive value favor single regime specification. Light gray, outperformance for Markov switching. Dark gray, outperformance for single regime, right? So the first thing we observe is that Markov switching dominates single regime in the case of normal distribution and a skew normal. But Markov switching with a normal distribution does not dominate a single regime with the student T distribution, right? Or skewed student T distribution. This means basically that the Markov switching mechanism is not able to account for the large kurtosis observed in the stock data. And in the case of MS-GARCH, student T or even skewed student T is required. So what we observe in this study is that the Markov switching mechanism in GARCH models really depends on the underlying asset class. So for stock data, there is a strong evidence in favor of Markov switching model, and this can be explained by the very large kurtosis and conditional and unconditional kurtosis observed in the data. This is not as strong for the stock indices and the currencies. And the second conclusion is that it is important to account for parameter uncertainty with this class of model in the case of stock data. So we are currently continuing, so this is a preliminary study. We are continuing now the research, and the next steps we envision is obviously the multi-step ahead forecast, because the impact of the mean reversion speed of GARCH versus MS-GARCH can be significant, right? So we know that we have a very fast mean reversion feature with the GARCH model. This is not the case with the Markov switching model. So looking at longer horizon will really give us insight about the forecasting performance, better forecasting performance of those models. Now we have parameterized the model such that all parameters can change across regime. The volatility parameters, but also the conditional distribution parameters. So we want to disentangle whether this is really the kurtosis feature or the volatility feature which makes Markov switching better. So this is something we want to investigate. Obviously, additional data sets. We are currently working on emerging data and commodities. And the last question will be to see what happens with the three-state Markov switching model and whether the optimal number of regimes, which could be obtained, for instance, with the BIC return, depends on the asset class. Okay, I want to thank a couple of people for their support. So Google Summer of Code, International Institute of Forecaster, FQRC in Quebec, Fonds Donation, Université de Neuchâtel, Industrial Alliance, and Calcul Quebec, because we run all the computations on very large clusters, so they were really helpful and helped us. The preliminary version of the paper is online on SSRN, and the package, which will be presented in a second by Kevin, is also on GitHub and on CRAM. So thanks for your attention, and I'm up for your questions.